All right, let's dive in. Today, we're heading straight into the engine room of modern software. We're going to figure out how the most complex systems out there manage to stay fast, scalable, and, not fall over all the time. We're going to demystify event-driven architecture and a really cool technique called complex event processing that literally turns chaos into intelligence.
So, think about it for a second. The apps you use every single day. Your bank pings you the instant a transaction goes through. Your food delivery app shows you your driver moving on a map in real time. What's the secret sauce that makes all of this happen instantly?
Well, the answer is a hidden world of beautifully organized chaos. Behind that smooth user interface, these apps are a constant storm of activity with countless little independent services all chattering away. The magic isn't in stopping the chaos, it's in how they manage it, turning what could be a total mess into a perfect symphony of real-time data.
Okay, so to really get the solution, we've got to understand the problem first. And that problem? It all starts with something I like to call the microservice maze.
See, back in the day, a lot of software was built as one big single piece, a monolith. Simple to wrap your head around, sure, but super rigid and a real pain to update. The modern way is to use microservices, breaking down those huge applications into lots of small, independent parts. Now this is awesome for moving fast and scaling things up, but it creates a whole new kind of headache. When every little service has to call every other service directly, you get this tangled web. One service hiccups, and it can set off a chain reaction, a domino effect. And trying to keep data consistent across dozens of tiny databases? It's a massive challenge.
So how do you escape this maze? Well, you have to completely change how you think. You stop thinking about services calling each other, and you start thinking about them reacting to things that happen. This is the event-driven escape.
In an event-driven architecture, or EDA for short, services don't make direct requests anymore. Nope. Instead, when something important happens, say an order gets placed, a service produces an event. It basically just shouts out into the void, "Hey everyone, an order was just placed." Other services, any that are interested, can then listen for that event and decide how they want to react.
And this one simple shift, it's a game changer. It solves our biggest problems. Because the service that creates the event and the one that consumes it are loosely coupled, the order service has no idea the shipping service even exists. This gives you incredible resilience. If the shipping service goes down for a bit, who cares? The orders just keep flowing in. It also makes the whole system super scalable. Getting slammed with orders, just add more listeners to handle the load. It's just a much more responsive and tough way to build things.
But just sending and receiving events isn't the whole story. Not even close. The real power, the magic, comes from finding meaningful patterns inside this constant flood of information. This is where we go from just being a plumber connecting pipes to being a detective looking for clues.
And that's where complex event processing, or CEP, comes in. You can think of CEP as the brain of the whole system. It's not just a mailman passing messages along. It's actively listening to all these streams of events, sometimes from dozens of different sources, and it's looking for specific sequences, for correlations that mean something important is happening. It's the difference between just hearing a bunch of random noise and actually recognizing a song.
Now, to find these patterns, we need to understand the difference between stateless and stateful operations. A stateless operation is simple. It treats every single event on its own with no memory of what came before. But a stateful operation, it remembers. It can keep track of information over time to see the bigger picture, like, say, calculating the average temperature over the last 5 minutes, or noticing that a user has clicked on 3 different pairs of shoes in a row. CEP absolutely depends on this stateful memory to connect the dots.
Okay, I know this might be sounding a little abstract, so let's make it super concrete. Let's look at how these incredible real-time powers are being used out in the wild every single day.
You see this stuff in action everywhere. Your bank uses CEP to spot fraud by detecting patterns, like your credit card being used in 2 different countries just minutes apart. Factories use it for predictive maintenance, analyzing data from sensors on machines to catch failures before they even happen. It's also absolutely critical for network security and, of course, for analyzing all the clicks on a website to understand what users are doing as they're doing it.
So defining a pattern might sound really complicated, right? Like it's some kind of crazy algorithm. But at its heart, it's really just a rule that you, the developer, define right in your code. You're just telling the system exactly what sequence of events you want it to look for.
Let's check out this example from a popular tool called Apache Flink. This one line of code here is a perfect example of a pattern.
We're telling the system, hey, start looking for a temperature event, but only where its value is 50 or higher, and I need to see that happen 3 or more times in a row. And right after that sequence, I want you to look for a smoke event.
And so, when the stream of incoming data finally matches that exact rule, 3 high temperature readings followed by a smoke event, boom! The pattern is detected and the system instantly fires off an alert. That right there is CEP in a nutshell, turning a messy stream of raw data into a meaningful, actionable insight.
Now, there are a couple of common ways to get these events flowing in the first place. On the left here, you see a pattern called change data capture, or CDC. You can think of this like you're tapping the phone line of a database. Every single time the data changes, an event is automatically created. Then on the right is a more direct approach, where your application's code is written to explicitly create business events, like order placed. Both are really powerful ways to build an event-driven system.
So remember that data consistency problem we talked about? In a world where there's no single central database, how do you handle that? Well, we use something called the saga pattern. Think of it like booking a trip online. You book a flight, then a hotel, then a rental car. Each one is a separate step. Now, what if the car rental fails? You can't just unbook the flight. Instead, you have to run a new transaction to cancel the flight, and another one to cancel the hotel. Those are your compensating transactions. The saga pattern automates this whole dance, making sure the entire multi-step process either succeeds completely or gets cleaned up properly if something goes wrong. Building these systems is obviously super powerful, but let's be real, it's also loaded with traps you can fall into. So for this last part, let's get into the architect's guide for getting this right. Yeah, building these systems isn't without its challenges. That state we mentioned, the memory of past events, if you don't manage it carefully, your app's memory can get totally bloated and everything slows to a crawl. And debugging? Oh man, because everything's happening asynchronously, it can be a real nightmare to figure out what went wrong without amazing monitoring tools. Even simple things, like not having strict data formats or picking the wrong way to partition your data, can create these silent performance killers that are incredibly hard to hunt down. So the best practices are really all about being deliberate and thinking ahead. You've got to create strong data schemas right from the start so there are no surprises. Use techniques like watermarks to tell your system how long it should wait for late data before it moves on and cleans up old state. Build in fault tolerance with checkpoints so you can recover from a crash without losing everything. Really understand your delivery guarantees. Is it okay if a message is processed at least once, or does it have to be exactly once? And finally, monitor everything. You absolutely cannot fix what you can't see. This Wordly map gives us a really fascinating look at the future. This kind of map shows how technology evolves over time. Things start out on the left as brand new, custom-built ideas. Then, as they mature, they move to the right and become stable, standardized, off-the-shelf products. And you can see that patterns we've talked about, like change data capture, are making that journey. They're moving from being these specialized niche techniques to becoming standard, commoditized parts of our toolkit. This tells us event-driven architecture isn't just a fad, it's becoming a fundamental industrial strength way we build modern software.
And that really brings us to the final big thought. We've built these systems that can react to the world, not in hours or minutes, but in milliseconds. They can find real meaning in the absolute chaos of data streams. The power here is just immense. It lets us go from just processing what has happened to truly understanding what is happening right now. So the real question we're left with is this. If our systems can understand complex events as they happen, what will they be able to predict next?